Hi everyone. So here we are. We're in week 8. We're getting close to the end. Um, I'm sure you're all feeling the way I am, that things are overwhelming right now. I can tell you as a parent, during COVID, people were surprisingly understanding. Everyone was at their limit and exhausted and tired and frustrated. I think the people that are probably suffering the most right now are students, teachers, and moms. Not to say not dads as well, that's not what I'm trying to imply. But there's this perception that COVID's over, even though everybody knows it's not, and that all of our previous expectations need to be back up to standards. So I know that I'm struggling with it myself. I have a lot going on with the kids, and but yet work-wise, everyone expects things to be normal. Teaching, they expect everything to be normal, and I'm at a breaking point, so I can't imagine how you guys are feeling. Anyway, I just want to let you know that it's hard for everyone, and I feel you. If something comes up or you need an extension, I'm usually pretty good at responding to that. This week, I have to be in Winnipeg. Today's Wednesday for me, so I'm recording this early in the morning on Wednesday. I have to go to Winnipeg this afternoon, and I come back on Friday. That means I won't have office hours this week. So if you're emailing me for an appointment or something, I'm not available this week. So I apologize for that. Today's lecture is one that I love, although you're going to be a little bit thrown off by it. I'm going to tell you a lot of stuff that you don't actually have to do any work for, simply because I want to give you some backstory for the stuff you're going to do. Because mostly what you're going to do today is pull stuff off of charts. But I need you to know that those charts came from somewhere. That's part of what is very important for your understanding. It's the understanding how those charts exist or what those charts are telling you that is the knowledge. But I don't want to make you have to do the math, because for every little number on these pages and pages and pages of charts are pages of calculations for every single number. And I don't want you to have to do pages of calculations to get an answer. So I have a compromise. I'll do all the hard work for you. You'll listen, try to get a general feel of what I'm talking about, and then I'll let you use the charts. But I need you to at least try to focus on getting a feel for what I'm saying. So you don't have to do too much work in this lecture, but I want you to pay attention to what I'm saying. Okay, by the end of today's lecture, we'll have answers. It'll only be for steel, but we will know if we have the properly designed member that works for our loads. Do we have a member that has a reduced capacity greater than the factored load that's applied to the element? Which is exciting. You're going to be able to do the job of an engineer now. You'll be there. You'll be able to say something works. Last week, we learned how to do sizing guidelines, which means it's probably going to be pretty close to the answer, but we're going to see towards the end of the lecture that it's a good place to start. We will have drawn something on the drawings that leaves us hopefully a buffer, but what we don't want is to find out that we actually need a bigger member than we gave allowance for on the drawings. Hold on a second. Sorry about that. We have the weirdest house with odd mirrors that show up in different spots. And so you just saw Dave come back from after his run in his sweaty running gear. So I paused it so the poor man could get stuff out of his closet, which is the front foyer of the addition of our house, because it's a bonkers weird house. And so the weird window, the weird window you can see is actually in front of me, is the original house to the main part of our house that looks into the addition. So there's weird optical illusions in this house all the time. Okay, so by the end of this, you'll have answers. Reduced capacity, greater than factored loads. So like I said, a lot of backup info so that you can do it the easy way by the end of the lecture. All right. We learned when we talked about stress and strain that the relationship between stress and strain is E, or the modulus of elasticity. And you guys already know the modulus of elasticity for steel, and that is 200,000 MPa. That's something you know now. Stress is force divided by area, and strain is the change in length divided by length, or the original length. And by combining these things, we have a bunch of equations that allow us to kind of, if we know a few things, we can solve for a different thing. We also, when we started talking explicitly about steel, looked at the full stress strain curve for steel. Remember, I love this diagram as a question. We know that it yields at 350 MPa, even though it has an ultimate higher strength, and that we have a linear elastic portion of our curve, or that's where if we load it and then unload it, it'll go back to its original shape. Beyond that, we have permanent deformation. We don't want to use our permanent deformation. We don't like the idea of permanently deforming our member. But if we did, we know we have this gigantic range of deformation plus a little bit of extra strength that would tell us long before we had a failure that we had a problem. And the act of this amount of deformation, here's the energy involved in our elastic deformation. This is the energy involved in the full rupture. So this is where I said seismic makes really good use of this ductility zone in steel. All right. We talked about axial loads, or axial stress and strain relationships 2 weeks ago. I'm going to jump to bending now. So I have my fancy foam block, which always looks distorted in these fisheye lens mirrors, or cameras. So a long time ago, a couple of polymaths, basically people who are smart about everything, kind of got together and came up with a theory. Now the Bernoullis were involved in thermodynamics and calculus. Euler was in all kinds of things as well. So really smart families getting together, and they developed a unified beam theory, or plane sections remain plane when you bend. Okay, so we've got our member here, and when we bend it, you can see that these lines stay straight. They don't curve. This line curves, but this line didn't. As we bent it, it compressed at the top and stretched at the bottom, but it did it by the same amount. So that plane section remained straight, and it, relative to this neutral axis that is curving, stayed at 90 degrees. How can that be? How can all of these planes that are staying straight be perpendicular to a curved element? Well, essentially we're turning it into a circle. At any one of those infinitesimal microscopic plane intersections to this neutral axis, we still have 90 degrees. I know, it seems crazy, but this is where calculus comes into play. We are talking about one infinitesimal plane. We're not talking about the whole length of the neutral axis. We're talking about that one plane. And you can see when we bend this, the 90 degrees stays the same. It distorts a little bit because this line is moving. But if I could draw my 90 degree mark even smaller, we would see that it wouldn't distort. So, premise number 1, plane sections remain plane. That 90 degrees stays the same. So, here's our neutral axis. Here's our plane section. That stays at 90 degrees. For beam-like elements, transverse cross-sections perpendicular to the neutral axis remain plane and perpendicular to the neutral axis. We keep it at 90 degrees. Step 2. For a plane section to remain plane, the strain must be varying linearly with the distance from the neutral axis. So, if this is bending, we know that it squashed here and stretched here, but stayed at 90 degrees to the neutral axis.
Coffee?
I would absolutely adore a coffee. Thank you. I forgot to turn the dishwasher on last night.
No.
So if we're squashing here and stretching here, but staying at 90 degrees to the neutral axis, we're getting some sort of movement here. We're getting compression here and stretching here. Well, we know that we can quantify that as strain. We knew where it was originally, and we can measure how far it's moved. And we're saying that that strain is varying linearly as you get away from the neutral axis. So the amount it's squashing goes from 0 to some big amount, and the amount it's stretching goes from 0 to some big amount. And the amount that that strain increases is linear. So let's look at that. We have our maximum strain here and strain here. Because remember, it didn't matter if it was positive or negative. It was how much it deformed divided by its original position. So we have some amount of strain here and some amount of strain here. And we know that if it's at 90 degrees, we have no strain right here. So that means we have a straight line for the strain. Does strain have a relationship to anything else? Yes, especially for steel. We know it has a great relationship to stress. So we can measure the strain, we can see it visibly, and then we can measure it. That means we can calculate the stress. Because remember, the relationship between stress and strain is linear through the modulus of elasticity. So if the plane sections are remaining plane, the strain is varying linearly, and then the relationship between stress and strain is linear, so that means the relationship from stress away from the neutral axis is also linear. So we're saying as we bend this, we're getting the maximum stress here where it squashes and stretches here. So we have the same stress top and bottom, and it is varying linearly with 0 stress at the neutral axis. So this was our strain. This is our stress. We have our maximum stress here and our maximum stress here and no stress right here. Well, if what we care about is not making this part of the element fair, we want to make sure that we don't fail our member, we don't want to go over our reduced capacity, well, we want to make sure that this part right here never hits 350 MPa. Remember, that's the yield stress of steel. If this part right here goes beyond 350 MPa, we're going to have permanent deformation. And we don't want that. We don't like permanent deformation. And we know that we would probably reduce this somewhat, so it wouldn't be 350 MPa. We'd probably do something reduced. We don't even know what that looks like yet, but I'll talk about that by the end of the lecture. Now, if we know that this is the stress profile and we want this part right here not to hit its maximum, maybe we can do something with this. So you can see here, I've just taken this and redrawn it with a triangle. It's still the same triangle. I've just drawn it on the other side. So the Euler-Bernoulli theory, if we look at a rectangle in bending, just as it starts to yield at the extreme fibers, we would have a stress profile that looks like this. So we're saying this is our element that we're bending. So we've got this right here. Look, it looks just... This is what is on the face of this plane right here. And we're saying we're going to bend this object like this, and we are cutting a plane through here. So This line right here is like we cut this beam and we're going to look at what's happening at the stress right here, just as if we started to bend it and we're just about to reach the maximum loads at the top and bottom. Okay, if you were in my graduate course, we would have to derive this process where we look at what that stress profile shape looks like. We sum the moments and we sum the forces on the top and the bottom of the neutral axes, and we develop a moment equation. Essentially, what it says, thank you, is that we have this crazy equation that has B and D in it. So B is the width of our element and D is the depth of our element. And it tells us that the moment is equal to our stress times BD squared divided by 6. Well, B and D are 100% dependent on the shape of our cross-section. So what does it look like in that cross-sectional profile? So we're saying B times D squared is our shape property to solve for moment. So moment equals stress times some shape property. We're just going to use S as a placeholder. S is a placeholder for a bending shape property. For a rectangle, we know that in elastic bending, that is BD squared divided by 6. So just as our steel starts to yield at the maximum extreme fibers, so at the top and bottom, we can figure out the relationship between stress and moment. In fact, I'll rewrite stress here in a few minutes. So we can calculate it with our understandings of moments and eccentricities and couples, but you don't have to. That's that slide I just showed you. S is a property based on the cross-sectional shape of the member in elastic bending. So this equation only holds true as long as we stay in elastic bending. That seems crazy. Why would I let us go into plastic bending if we don't like permanent deformation? All right, let's think about that now. But the cool thing here is we know that we don't want this to go over 350 MPa. Moment is dependent on the loads on the element, and S is a shape property of our section. And we're picking our section. So we could possibly figure out what capacity this element has. We know its shape, which means we can figure out its shape property, and we know what the maximum steel capacity is. That would give us the maximum moment capacity of our element. So if we knew what our factored load was, or our factored moment, if we put a reduction factor on this, we would know our reduced moment capacity, and we could tell if it was greater than our factored moment on the element. Well, look at stress. Remember, we wrote stress as force divided by area? Well, we can rewrite that moment equation as stress equals moment divided by shape property S. They're the exact same. Stress, which we know for steel is 350 MPa for yielding. Force type, shape property. So both of these follow a very similar equation setup. Okay, this one always throws people off because it really only applies to ductile members. I wouldn't even do it in this lecture, except it's the best place for it because we're talking about steel, but it isn't a thing that applies to our other materials. Concrete is brittle and wood is brittle. So this second part doesn't apply at all in the least bit to those materials. Okay. We said that we want to limit the stress at the top and bottom fiber to just when it starts to yield. We'll let it go right to that point, but beyond that, we'll have permanent deformation, which is true. But do you remember in that stress strain curve, when you were getting permanent deformation, you weren't increasing the stress at all. What if just a little bit we allowed it to have some small amount of permanent deformation all the way until we got our maximum stress all the way down here? So remember that thing, plane sections remain plane? Well, that's true until it starts to yield. Remember our stress strain curve looks different? So we're saying, okay, at the top and at the bottom, we'll allow some small amount of permanent deformation, and now we'll allow the stress, the maximum stress, to come all the way down to the neutral axis. Beyond that, and we definitely failed this member. But what we're saying, and when I'm doing this in real time, I'll often redraw this stress profile. Let me, it's dark in here, so I don't know how well this will show up. What I often do in my grad course is when we do this, I draw the stress profile. I'm going to draw it on the other side just because I find people understand it better. Okay, we're limiting this to our maximum stress, top and bottom. Right? Well, we're going to say that we'll allow it to have some amount of permanent deformation. Maybe we come down like this a little bit. Oh, I went a bit further with that one. And then that becomes our linear elastic zone. So right here, we're getting some permanent deformation, but we still have zero stress down here at the neutral axis. And then we say, okay, we'll let ourselves go even just a little bit farther, just the tiniest little bit. I just want to, sorry, I've been drawing those arrows backwards. I wasn't even thinking. These are going in opposite directions. We're going to let this now come just down to the neutral axis. So this is just a redrawing. That is just a redrawing of this. So we're letting our maximum stress come all the way down to the neutral axis. We don't want to go beyond that, or else we're going to have a lot of permanent deformation throughout the entire member. But we'll say we'll let just a tiny little bit of permanent deformation happen, just as we get that maximum stress or that yield stress down to our neutral axes. So if we did the same thing I did before, that thing you don't have to do, where I look at what that stress profile looks like as a block, and I look at the internal forces and rewrite it as a force and a moment, because we know about couples, then I can go through and figure out that the moment equals the stress times the width, b, times the depth, d squared, but divided by 4. So it's just a different shape property. Before we had s. Well, now we're saying if we let it yield down to the neutral axes, so we say, okay, we'll let it go past the extreme fiber, we can use a different shape property called z. Z just lets us get a little bit more out of our steel beams and columns because it has the ability to yield, and it has a very large plastic zone. Wood and concrete, we can't make use of Z because it doesn't exist. It has a brittle failure mode. So as long as just as our steel starts to yield at the extreme fibers, that one should actually be changed. So we'll allow our stress to go all the way down to the neutral axis. So slide 13. I'm just going to rewrite what's written there. And so Z is again a shape property based on the cross section, and we're checking to see what member works so we could look up what the shape properties are or calculate them. And remember, for a rectangle, S was BD squared divided by 6. And for a rectangle, Z was BD squared divided by 4. So it seems like for a rectangle, it's pretty darn easy. So that both equations are still similar with our yield stress equal to the type of force divided by a property dependent on the shape of the section. So this one just lets us make a little bit more use of the fat of our steel because we know it has a huge plastic zone. And we're only just going to touch the tiniest little bit of it. All right. I thought I heard a kid, but I do not. It's the heat coming on. There is another thing that we can calculate looking at this Euler-Bernoulli strain beam theory. Remember, I just briefly touched on strain simply because it allowed us to talk about stress because we knew those had a linear relationship? Well, if we talk about the strain itself, we know that this angle can be calculated based on how much strain we have here. Well, with that, we can go through all kinds of stuff, which actually involves a double integration. Don't worry, not even close to what we're going to do. But I am going to tell you that it allows us to calculate what that angular strain is as a relationship to the moment. And that angular strain is moment divided by EI. E is our modulus of elasticity that talks about basically the slope of this line. I is a shape property. Well, it's just another shape property that is a part of or related to this angular strain of the element. So BD cubed divided by 12. One more shape property that I've given you. So today, you guys have always known about area. Most of you would even know how to calculate the cross-sectional area of most shapes. S is a shape property that has to do with elastic bending. Z is a shape property that allows us to make use of the plasticity of steel. Doesn't apply to concrete and wood. And I is a shape property that is related to basically the deformation of the element or the amount it's going to deflect. So I is BD cubed divided by 12 for a rectangle. So we're talking about some really big kooky numbers here. All right. So I'm just going to show you those slides that I said you don't have to worry about. Start with angular strain, we can integrate, we can get the rotation at any point, we can integrate again, and we can get deflection. Now, you do not have to do this. In no way, I'm not even showing you the calculations for this. But the deflection of a beam, so if this is our beam and bending, and we've deflected it, the amount of deflection that we got there at the middle, the amount of this deflection right here is equal to 5 times W, which is our linear load on our beam. Now this is just for a simply supported beam with a uniformly distributed load on it. Do you remember way back when I said that was like the most common type of beam we'd ever seen? So W is our load, L is the length. Why they write length of beam in a lowercase for deflection when everything else in the world they write it as a capital has always bothered me. Don't you find that they always write deflection L as a lowercase l? So it kind of looks like it's not L. Anyway, this is really this is the length of our beam to the power of 4 divided by 384 EI. I we know is a shape property. E we know is the the modulus of elasticity of our material. This is a load that we can calculate based on the tributary area. Length, well, we're talking about a beam in a building that we're designing, so we know the length. So we can figure out the loads. We know the length. We know the modulus of elasticity of steel is 200,000 MPa, which means that all that's left is this shape property I. Well, we know if it's a rectangle, it's BD cubed divided by 12. But maybe we could calculate that for any shape if we needed to. So, do you remember axial strain could be delta L equals PL divided by EA? Remember that way back when we were talking about axial stresses and strains? When we knew that E equaled, or that modulus of elasticity equals, let's go back here for a sec. Let's see how far back we have to go. Just want to bring you back to this slide. Remember, so E equals stress divided by strain, stress equals force divided by area, strain equals change in length divided by original length. We could plug PA in for stress, delta L divided by L for strain, and we could rearrange it, and we got delta L, where our change in length equals our force times our length divided by our modulus of elasticity divided by A. A is a shape property. We don't talk about it that way very often, but A is a shape property. Let's come way back down. Well, this is our axial strain, and this is our bending strain. This is our deflection at the midpoint of our simply supported beam. The delta L was axial force. So we're talking about deformation, force. It's just a particular, we're just writing it a slightly different way. Length, E, shape property. So even though they look very different, this one has a bunch of constants in it, they're really fundamentally coming from the same place, these two equations. Both talk about deformation, both have a load applied to them, both involve the length, both involve the modulus of elasticity, and then both involve a shape property of the member. Well, I have just shown you, actually I even showed you how to derive S and Z, even though you're not going to have to. And I showed you how some people might go through the process of deriving I for a rectangle. But look at this. Here's a handy little chart. For a rectangle, it's easy to calculate. No big deal. If we're talking about elastic bending, BD squared divided by 6. Super easy. What if it was a more complicated shape? We would know we could probably calculate all of that. But what if we've done this so many times throughout history? When I say history, I'm talking about the past 150 years. What if somebody's already calculated them for us? So for an I-beam, I don't know, that looks like a W section, the sections that we use all the time for elements in bending. I, they've calculated it here. S, look at this. They still have that 6 involved. We have the depth, which is the overall depth. B is the width. And then they've added W and T. Well, W is the width of the web, and T is the thickness of the flange. So it looks like if we know all the other stuff in the equation, and the shape properties are the only thing we don't know, we could probably figure that out. Well, look at this. I'm giving you charts for all kinds of shape properties. I think I forgot to upload shape properties for you. So I'll upload that right away as well. So if we can calculate a shape property for pretty much, if we can calculate S, Z, and I for pretty much any shape out there, we could maybe start to do something with these equations that we're seeing written out now. Well, look at this. Even for those W sections, maybe we know we could calculate it, but what if it was even easier than that? What if somebody has already calculated these because there's a shop that makes all of these steel beams to be identical or pretty darn close to identical to each other? What if they had that in our chart for our members? Well, look at this. Here are W sections. Remember we talked about mass last week and we talked about B and D? Look at this. They have T and W in these charts as well. But look at what they also have. I, S, and Z. So they've already calculated these shape properties for us. You can see here that these are all called about the x-axes. So they call it IX, ZX, or SX, and ZX. Look at this little diagram here. This is the X. It is telling us that we're talking about things about the neutral axes. So if this is my cross section, and in this one I've got B and D, if this is my beam in bending, you can see we're talking about moment about some axes here. We're saying we're talking about moment about this line in the element. It's internal axes like this. So we're talking about moment about this line. So remember, if we curled our thumbs, we're talking about it going around this x-axis. If we had something, so this would be our strong axes bending. What if we had something bending sideways like that? Well, if we had something bending sideways, we might want to know those shape properties about this axis, because now we're talking about it in this, bending in this direction. So for that, we would want to talk about it spinning about this axis. Remember my thumb, this is the moment being applied to it. My thumb is the axis. They call this the internal y-axis of an element. So x-axis, y-axis. Bending in this direction, we're talking about the x-axis. Bending like this, we're talking about the y-axis. Well, if you guys remember, we looked at those loading diagrams for different beams way back when. We had where you could calculate R and V and M. Well, they also had one for deflection. And within it, they had the shape property I. So if we had a simply supported beam with a uniformly distributed load on it, which I said that this beam right here is probably 95% of beams that ever get designed, uses these equations right here. Well, here is the equation for that. It's printed so small I can't even read it on this. You guys can open the PDF, but I know it is deflection equals 5 WL to the power of 4 divided by 384 EI. You don't need to memorize it. You can look it up in the chart, but I tell you, I plug that into a calculator all the time. Even though I have fancy design software that does all kinds of them for me, sometimes it's easier to just plug it into my calculator and double check it. You guys, though, have access to this diagram right here. So you know that you can calculate I or figure out I for any given shape. You can look it up. You know the length of the member is how long it is, and you know W is the load. We're talking about deflection. Are we still talking about a factored load? Do we care about our factored load when we're talking about deflection? No. Remember, strength is all about factoring. That is a life safety requirement. We want to reduce our capacity and factor up our load. Well, deflection didn't even seem to have anything about capacity written into it, which seems a bit weird, but whatever. It just had its deflection performance written into it. So what we care about there is serviceability. So we are not going to use factored loads when we're talking about serviceability. Do you remember way back in the course? And I talked about how you should track your factored loads for load cases, but also keep track of your serviceability load cases. And you're like, why would we do this? Why do we need 3 different load combinations that are important? Well, we're going to use strength for shear and moment, and we're going to use those serviceability load cases for deflection. Don't worry, I'm going to go through a full example, and my hope is I'm going to go through, we're going to do examples in this. You have an assignment, but what I would like to do this week for you is produce a few more handwritten examples that you guys can take a look at, just for people who like extra practice problems. I say that I always try to add more examples each year, and this is a lecture that only has a couple examples simply because it takes so long to get through all the material. But for you guys, I'm going to try to produce a few more this week, just so you have some worked out examples at your fingertips. All right, what is the number one super duper important thing about bending? Length and depth have the most important impact on design. They are not linear, as much as we try to pretend they are for rules of thumb. Remember last week I told you that for sizing guidelines, the depth of our member equaled the length divided by some sizing guideline. And that is a linear relationship. And remember I said that's great if we're talking about a small range of narrow, normal applications. And I said that this week we would find out that in truth they are not linear related. This is what we have done. We have just talked about this. So, length for the load, for the life safety, M equals WL squared divided by 8. That square is not linear. As something gets longer, there's more and more moment. And it is not a linear relationship to the load. So, load is linear. Double the load, double the moment. But double the length, you square the length increase in the moment. So it's not a linear relationship. Deflection. Look at length written in deflection. It's to the power of 4. It has a huge impact on deflection. So if you increase the length, it's not a linear impact on the deflection. It's a to the 4th power impact on deflection. So L squared for strength, L to the 4th for serviceability. Depth. Now, I'm talking explicitly, I'm using the example of a rectangle in cross-section, but these constants tend to hold true no matter what. So, BD squared divided by 6 for strength. B is the width, and it's linear. Depth of our cross-section is squared. It is not linear. So, if you deepen your member, you don't have a linear increase in your section property. You have a squared impact on your section property. I, remember, which is related to stiffness or the deflection of our element, BD cubed. Width for both of these shape properties is linear. Double the width, you double the capacity. Double the depth, you don't double the capacity, you square the capacity. You cube the capacity for deflection. So, depth and length have the most impact on design. If something doesn't work, if you go through everything we're about to do and you find you have something with a reduced capacity that is not greater than the factored load, us as the designers have to make a change. We can make something wider or narrower. We can increase or decrease load, but those are going to have a linear impact on our design. If we really want to make a change, if we really need this to work, we can shorten the span. If we shorten the span, we don't have a linear impact on its capacity. We are going to have a squared capacity on its a squared impact on its capacity. If its actual deflection is surpassing our allowable deflection, if we shorten the span, we don't have a linear variation in its deflection. We don't improve its deflection linearly. We, to the power of 4th, improve its deflection. Depth, if we have a beam that doesn't work, well, maybe we can't change the length. That's set. Our grid lines are set. We could deepen our beam. And we don't have to, if it's overstressed by 2, we don't have to double the depth because we have a squared increase in our capacity due to depth. So whether it's length or depth, we have an impact on strength and serviceability. So remember our old friend, this equation. Let's even just jump to the next part. Let's get down here. We want our reduced capacity to be greater than the factored load. If we see the subscript F, we're talking about factored. And if we see the subscript R, we know we have our reduced capacity. For serviceability, we're not going to do this, and we're not going to do this. Because that's not about life safety. That's not strength. All right. We talked about our steel properties last week. Let's just brush them up here a little bit. Fy is 350 if it's an HSS or a cold formed section, 345 if it's a hot rolled section. What's Fy? Fy is just that maximum yield stress on our stress strain curve. If what we care about is not exceeding this limit, well, who cares if we're at 250? Great, it works. We're not going to check it against 250. We want to make sure we don't exceed these values. These are the values we care about. If we're less than that, we're fine. We're in a zone that works. If we go over these elements, that's when we have a problem. I've talked a lot about reduction factors or reducing the capacity. Here are the steel reduction factors. So for normal steel, whether we're talking about a column or a beam, we're going to reduce our capacity by 10%. We're going to make it only 90% of its capacity. Really what we're saying is we're going to reduce 350 or 345 by 10%. We're only going to allow ourselves to use 90% of these capacities. Rebar and bolts and shear connectors and anchor rods, we have some slightly different values, but this is really the only one we're going to talk about right now. When we talk about concrete in a few weeks, we'll talk about rebar. Okay, let's actually do some design now. We're ready to do a calculation and start thinking if these things work or not. Well, actually, I'm going to show you how to use a chart to do the work for you, but we should talk about where these charts come from. All right, tension is pretty easy. Steel behaves nicely in tension, and we don't see weird things start to happen. And I'll talk about those weird things when I talk about compression in a second. So tension design is all about the cross-sectional area. So TR, or the reduced tensile capacity, remember this R means I'm talking about a reduced capacity, which means I should look, yep, there's my reduction factor, fair enough. I get to put my little subscript R here because I have this reduction factor in it. TR equals our reduction factor times the cross-sectional area times Fy. Remember, Fy is the maximum stress I want to let my object see. We know for steel that we want to reduce the capacity by 10%, only 90% of it, and we know A is the cross-sectional area. So for any given moment, for any given member, we can calculate the tensile capacity of it, the reduced tensile capacity of it. Compression's harder. Okay, let's talk about why. I've got this beautiful column here. If I stretch on it, you can see that there's some deformation, and it's easy to understand that if I had bigger hands or I could apply the load better, you could see that it would be evenly distributed across the cross-sectional area. A column. Okay, what happens when I try to squash this column? That doesn't seem like it has anything to do with how strong the material is, because it doesn't. It has to do with its slenderness or the fact that it wants to buckle, all right? So a column isn't just dependent on its cross-sectional area. It is dependent on its ratio to length to cross-sectional area. And there's two directions that this could happen. Now, it's a lot harder to do it in the other direction. So, compression design has two components to it. It has, is the material strong enough to take that compression load? No problem. We know that would, I just want to block all this out. We're left with reduction factor A, Fy. So Cr is the reduced compression capacity of our element. If you ignore whatever this weird stuff is, this looks exactly like our tensile capacity. The equations look the same. But that just has to do with the material strength of our element. We need to think about how we talk about buckling. Because look at this. If I make this really short, it doesn't try to buckle anymore. It just tries to squash. And that is this part of the equation. Make it really short and it's trying to squash. Great, we've got that right there. We know that's all about the cross-sectional area. But if I make it longer, it just tries to buckle. And what happens when it's somewhere in between? It squashes and then it buckles a little bit. So it seems like we have this range. Make it really short and we care about squashing. Make it really long or tall and we care about buckling or slenderness. And make it somewhere in between and it's some combination of squashing and buckling that we have to worry about. So here's our reduction factor. We know for steel what it is. Cross-sectional area we know is a shape property. Fy is the yield strength of steel, which we just don't want to exceed the yield strength of the steel. Lambda. Lambda is KL divided by R times the square root of Fy divided by pi squared E. I know, a pain in the butt. Well, R is another section property. If you looked at those steel shape properties, we had something called R in there as well. We're not going to worry about it. You're not going to calculate it. But this is all about its ratio of length to its cross-sectional area, essentially. R is really saying how far away is the worst point from the center of our column, because that's going to tell us its ability to resist buckling. So lambda is really just this ratio of how long is it to how big is our element. So really, you can call this your slenderness ratio if you'd like. K is really just saying what our member looks like, or how is it trying to buckle. So this, you can see, is buckling by allowing it to rotate at the edge. See how this flat plane has rotated? It doesn't stay at 90 degrees to the load being applied to it, and we get this buckling shape. What if I moment connected the top and the bottom, but I still tried to put that load on it? Well, look at the shape of how it's buckling now. You can see the top. It's hard because it's a foam block, but you can see the top is more perpendicular to my hand, as is the bottom. And it's actually hurting my arms to do this because it's a lot harder to buckle it. Because what I've done is by moment connecting it, it is similar to having a shorter length member. So K is how does it move based on its connections, or its kind of connection factor, if you want to think of it that way. We also say that we don't care what load it can take, even if it says it doesn't buckle. If this was like 30 of these stacked high, actually less than that, but if this was several of these stacked high, it could take some amount of load before it buckled. But when it gets so slender relative to its height, we say, you know what? The smallest load could make that buckle, and we don't want to take that risk. So we're going to say at that point, it has zero capacity. So if that length relative to its slenderness or its cross-sectional area is greater than 200, we don't care. I feel like I hear an alarm going off. I'm hearing things. So we're saying that we don't care if it can take a little bit of load. It doesn't matter, full stop. It is too slender to even reliably take any load. So here is that effective length. Here's that drawing that I told you. This is what we say most of the time it looks like. And it's got a factor of 1. That's what you're going to do. It's always going to be 1. In fact, you're not even going to calculate this, so it almost doesn't even matter. But I want you to see where it comes from. And then with a column, you can see if we grab the ends and moment connect it. Remember, this is what our moment connection symbol looks like. Here's a pin. Here's a moment connection. We can see it's kind of like this is the length of the element. We've shortened the length of our member. All right, what if I took a particular column and I said if it's really short, what capacity does it have? So I calculate out how much capacity it has. And what if I just thought about the fact that it was based on its cross-sectional area? So reduction factor times Fy times the cross-sectional area. Well, length isn't in that equation. If my column is really, really, really short, here's the capacity. If my column was really, 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 really tall, here's the capacity. It stays the same. It is independent of length. But we know that columns, as they get slender, like to buckle. So I can calculate the critical buckling load of a particular column at different heights. This line keeps going up off the page. So for a really, really short column, it's impossible to buckle it. When it's short, all it wants to do is squash. I know that is actually squashing. If you could see the way the whole thing is behaving, it's not buckling, it's squashing when it's really, really, really short. As it gets longer and longer and longer, or taller and taller and taller, it buckles at a very little load. Like, look at how little load it takes to buckle this. So this is the load that it would buckle at, and this is the load that it would squash at. So it looks like when it's really short, it's only going to want to buckle. And when it's really tall, it would fail. Sorry, when it's really short, it would only want to fail by squashing. And when it's really tall, it would only ever want to buckle, or it would buckle long before we got close to our squashing capacity of our element. So what we've said is, obviously, when it's really short, it's governed by squashing. When it's really tall, it's governed by buckling. In fact, it's so governed by buckling, we're going to say there's a point where it's so tall and slender, screw it. It can take no load. Even though we could calculate that it could take a tiny little bit, we're going to say nope. We're saying it can take absolutely no load. In between those two zones, we're going to develop an equation that is some part squashing, some part buckling. And that was what this was right here. This lambda was all about that combination of buckling, or that tendency to buckle. This diagram makes another fantastic exam or quiz question. I like this. I like these pretty diagrams. Okay, so I've shown you that big complicated equation. What if we say we have an HSS 127 by 4.8 and it's 2 meters long? Well, we could go calculate the capacity. And then we come to another column and we have an HSS 127 by 4.8 that's 2 meters long. I just checked it. Why would I calculate the capacity again? I've already done it. Well, if we have a series of elements that are fabricated in a shop and we know that they get made almost identical, maybe we could calculate those capacities so that we could look them up in a chart so we don't have to do it every single time. And we could check it at the different lengths of it. Well, that's exactly what I've given you, is the column design tables. These column design tables show the compressive capacity of steel columns at a range of heights. So let's take a look at our very first one, an HSS 127 by 4.8 at 3 meters and 975 millimeters, so 3.975 meters tall. So almost 4 meters, pretty darn close to 4 meters. If we, let's see if I can open it here. I'll bring it over to the other. just bring up the page for you guys. All right, so I have posted for you guys a series of steel column tables. It's all in one PDF. Let's find our HSS 127 by 4.8. All right, we've got a round HSS 127 by designation, 4.8. So there we go. Oh, look at this. 350W steel, reduction factor 0.9. So they've told us that they've incorporated the reduction factor in this. In fact, factored axial compressive resistance, so CR. They have told us that they have used the reduction factor, and they've even let us know what reduction factor they used. So this CR tells us we're talking about reduced capacities, and we can now compare this to the factored load on our element. So HSS 127 by 4.8, and they asked us to check it at just shy of 4 meters. Ooh, look at this. Effective length KL in millimeters with respect to the least radius of a gyration. So they've told us, they've thought about R. Remember, R was the radius of gyration. And KL was that slenderness kind of shape movement of how it would deform. And for us, most of the time, it's going to be 1. But they're telling us in this table that they thought about all of the things that are in that equation. All right, 4.8, 4 meters. Oh, look at this, 272 kilonewtons. So it has a CR of 272 kilonewtons at 4 meters. We're a little bit shorter than 4 meters. Does that mean our capacity would go up or down? Shorten the column. Do you increase or decrease your capacity? Well, let's take a look. If our column was 2 meters tall, we can take 484 kilonewtons of compressive load. So if we have a column that is 3.975 meters tall, it looks like our compressive capacity would actually be a little bit greater than 272. Doesn't matter too much if our load, or maybe our applied load is 100 kilonewtons. Well, 272, whether at 4 meters, no problem, it works. If we shortened the column, we'd only increase our capacity, so no problem, this column works. What if our applied load was 272.2? We're a little bit over. Our factored load is just a little bit higher than 272, which is our compressive resistance. But we know that it wasn't actually a 4 meter tall column. It was 3.975 meters tall. So we could interpolate in between 4 meters and 3.6 meters and find the capacity for our exact member. So let's take a look at what that looks like. So here we can zoom in, which I just did in the PDF. You can zoom in and we can find that we're going to be somewhere between 309 and 272. We know we're pretty close to 4 meters, so we're going to be closer to the 272 than the 309. We can interpolate between those two things, and we get that our compressive capacity is 274.3 kilonewtons, or our HSS 127 by 4.8 millimeter column that is 3.975 millimeters tall can support 274.3 Arnolds, or 274.3 kilonewtons. If we knew what the factored load was on this element, we could say if it worked or not. Okay, let's do a quick example and then we'll talk about bending. We're designing a steel canopy for an existing building in Brampton. The height of the canopy is to be 4 meters tall, so they're telling us how tall our columns will be. The snow load is 1.44 kPa for ULS and 1.30 kPa for SLS conditions. The dead load is 0.76 kPa. Okay, so they've told us they've already figured out the snow loads So they've taken SS and SR and figured out what the actual snow load is. And in fact, they've told us for the two different loading types. They've told us what our ultimate limit states snow load is and our serviceability snow load is. So that's stuff that we learned how to do. We know we could have done that. We could have calculated that because we knew it was in Brampton. We could have done that process, but they've been nice. Somebody has already figured what the snow load is on this project for us. We're being asked, what size do we get this column needs to be based on sizing guidelines? So what we talked about last week. And then they're asking us, what does a 150 by 30 column work? So they've asked us explicitly to check a particular column. And then we've been said, in case we don't like that W section architecturally, what HSS would be the best? Remember, the best means it has to work, meet the design criteria. So they're telling us if it's an HSS is the design criteria. And after that, the best means cheapest. Because we want to use the least amount of steel we can. A, because it costs less, but also we could start to think about it on an environmental level. We want to use less materials if we can. So let's go through this example. I'll pull this up. Let me, oh, you can hear my stomach growling because again, I've been up since 3 a.m. and it is 6:40 and all I've had is half a cup of coffee. Not that that's a hint or anything.
Do you want the other half cup of coffee now?
I wouldn't want to eat right now anyway, although you guys can probably hear my stomach growling. I am very hungry, but I want to get this done before the kids wake up because I still have to pack, get groceries, put together a kid's Halloween costume, get ready for somebody to stay in my home for 2 nights, and then head off to Winnipeg, all before 10 a.m. Okay. All right. We know we have a column that is 4 meters tall. We've already been told this. Actually, you know what? Screw it. I'm not going to do it this way. I have a way I always like to do it. This is a good time to set up the process. So, column. I always write out everything I know. So, what we know. We have a height of 4 meters. We know we have a snow load of 1.44 kPa and 1.3 kPa for ULS versus SLS. And we need to find the size based on the rule of thumb. Does a W150 by 30 work? And what square HSS works? Okay, let's start with the sizing guideline. The sizing guideline for a steel column is height divided by 20 equals D or W, or the width of it. We have a height of 4 meters, which we know equals 4,000 millimeters. So W equals 4,000 divided by 20 equals 200 millimeters. Well, 200 millimeters doesn't help us all that much. If we were talking about an HSS, we would need something, well, this tells us we probably shouldn't draw a W150. So, because that has one side that's 150 millimeters in dimension. But let's talk about the HSS. I would probably suggest then an HSS 203 by 203. I can't be more specific than that because the thickness is irrelevant, has nothing to do with this very preliminary calculation. So if I was just at a preliminary stage in this project, I would say we should be drawing a 203 by 203 HSS for this project as a placeholder. The engineer will come along and do the design, but I don't want to find out I don't want to draw an HSS 152 by 152 and find out I needed a 203 by 203. Maybe that was critical on how far apart we placed the columns because cars needed to pass through. Maybe there's a truck that needs to back up to this door. So we would rather make sure we always draw something slightly bigger at this stage than something too small because we could get some unpleasant surprises later. All right. Step 2. We need to figure out what the load is. So the sizing guideline had nothing to do with the loading. So let's figure out our factored load on the roof. Well, they already gave us the snow load and the dead load, so we can check our load combinations. Ultimate dead is 1.4 times our 0. Up here, I forgot to write the dead load. So we have 1.4 times 0.76. Ultimate dead snow is 1.25 times 0.76 plus 1.5 times 1.44. We don't have a live load, we don't have any wind load. It only looks like we have dead or snow or dead and snow together. So let's calculate those. My calculator does not seem to be working very well lately. Wonder if my phone will be better. So we have 1.4 times 0.76. Our factored dead load case would be 1.06 kPa versus 1.25 times 0.76 plus 1.5 times 1.44 equals 3.11 kPa. Okay, so we know that this isn't the load case that governs, this one is. If it works for this, it works for this. So for all factored load cases, we're going to use 3.11 kPa. So for everything strength related, we're going to use that. But we also had to think about some serviceability load cases as well. Doesn't seem like they're asking about it much here, but it might matter when we talk about something else. So I'm going to track it right now. So we have serviceability dead and snow together, and serviceability snow all by itself. Because we know in our deflection criteria that we did, I think it was in the very first week, we worried about dead and snow or dead and live together, but then we worried about live or snow all on their own. They've told us they've already applied the serviceability factor to our snow load. So this would be 0.76 plus 1.3 kPa. And then this would be 1.3 kPa. So 0.76 times 1. What's wrong with my calculator? It's driving me nuts. 1 point. So, sorry. I'm very tired. Okay, 0.76 plus 1.3 equals 2.06. With these, it is not a question of which one is greater. Of course this one's going to be greater. There was no factors applied to it. But the criteria for dead and snow together is different than the criteria for snow by itself. So we need to make sure that this is less than the reduced capacity for strength elements, and we need to make sure that these are less than any serviceability requirements that we have for dead and snow together or snow by itself. Columns, we don't really have any serviceability requirements on them, so it doesn't seem like this was much use for us. Maybe we'll find it helpful later on. Let's take a look at that diagram. Okay, we are designing these columns right here. So we need to know what tributary area these columns pick up. Remember, we've got the factored load on this element, but now we need to know or on the roof, but now we need to know how much of that load goes to this column. Now, if this was a table, you would know that a quarter of it comes over here, a quarter of it comes over here, a quarter of it goes back here, and a quarter of it goes back here. What we're saying is that this column is picking up half of the load from this beam, and this beam is picking up half of the load from these joists. So each one of these joists, half of the load goes to this beam, and this beam, half of the load that it's picking up, which is half of the joists, goes to this column, and half of it goes to this column. So, load on column. Our tributary area is, we have 6 divided by 2 times 5 divided by 2. We plug that into a calculator. Our tributary area is 7.5 meters squared. So that means, remember, this is a factored load that we're using. So CF, our factored compressive load on this column, is 7.5 meters squared times 3.11 kPa. If we plug 7.5 times 3.11, we get 23.3 kilonewtons. So that column is supporting 23.3 factored kilonewtons on that's what it's supporting. We need a column with a compressive resistance, reduced compressive resistance greater than 23.3. So we need this to be less than, we need this to be less than the capacity of the column. So we need that to be less than CR. That's what we need. We want something that has a CR greater than this. All right. So let's check out our W150 by, what beam did they give us? By 30. For H equals 4 meters. Let's drop this image down a little bit. Okay, so this was our HSS here. Let's see if we can find the W sections in this. I'm just gonna go back a few pages. Ooh, W sections. All right, they've asked us about a W150. Let's keep going. Oh, past it. W150. So factored axial compressive resistance, CR, so the reduced compressive capacity of a W150 by 30. If it is super duper ridiculously short, based on just squashing, it can support 1,180 kilonewtons. Do we have a column that's that tall? No. It looks like it starts to lose capacity somewhere around 2 meters tall. And we have a column that is 4 meters tall. So let's come across here. It looks like 476 kilonewtons is our reduced capacity for this element. So let's bring this up here. Okay, so for our W150 by 30 with a 4 meters tall, CR equals 476 kilonewtons. Remember, CF was 23.3 kilonewtons, and it is, in fact, less than CR equals 476 kilonewtons. So yes, works. In fact, I will often put a square around something. So if somebody came along and was looking at this work, they could see instantly out of all of this stuff, because this was all the supporting information, yes, this works. Well, in fact, remember we said we want the cheapest element we can as long as it works and looks good? This is a lot bigger than it needs to be. It looks like we've got a really small load, and that is a really high capacity. Maybe there's something better. And in fact, they've asked us, what HSS works? What is the cheapest, lightest HSS that will work? So let's come back to our column tables. And let's move forward to the HSSs. And they said square, so we're just going to skip right over the other ones. Okay, a square HSS, CR. Well, we have a 4 meter tall element. Oh, it looks like these don't work at all. So a 2 inch by 2 inch and a 1.5 inch by 1.5 inch. They don't even have capacity listed if they're 4 meters tall. That seems like we are past that KL over our less than 200. So remember, it had to be less than 200. It looks like we're over that. It's just so slender that even if it could take a little bit of load, we don't trust it, and we're going to say no load, not at all. Let's come to the next page. Oh, look, we've got some information listed for a 4 meter tall element. Let's come along. Well, we could use a 76 by 76 by 160 by 9.5. It would work, but look at its mass. It's 18.1 kilograms per meter. Remember, that's a good indicator of what the relative cost is. If we could find a member that works that was lighter, that means it would most likely be cheaper. So let's take a look. It looks like the HSS 64 by 64 by 3.2 has a CR of 45 kilonewtons. That's lighter than the 76 by 76. So that seems like a really good choice. We have HSS 64 by 64 by 3.2. CR equals, what is it? 45 kilonewtons. And it is greater than CF equals 23.3 kilonewtons. Yes, it works. So it looks like the cheapest, oh, I'll make that bigger for you guys, sorry about that. It looks like the cheapest HSS that works, the cheapest HSS that works is a 64 by 64 by 3.2. So we have an answer. For that canopy that we were just looking at, let's bring that up again. For this canopy, the cheapest column that's going to work is an HSS 64 by 64 by 3.2. And we know that its reduced capacity is greater than the factored load applied to it. Here it is worked out. Okay, let's talk about the same thing, but with bending now. Bending looks more intimidating, and there are a few more things we have to calculate, but the premise is identical to everything we just did for compressive loads. So don't get too overwhelmed because they are very, very, very similar. So bending resistance. So this is MR of a beam. You are not going to have to calculate it. The equation looks like this. In fact, I might even just jump through to the end. I don't want you to have to worry about these calculations or what these equations look like, but I want you to see that they look similar to the column equation. So we have our reduction factor of 0.9. Mu is the buckling moment at the unsupported length. Or do you see this here, this 1 minus stuff? That looks very similar to our lambda. My is the elastic moment with no reduction factor. So that is, we've got a reduction factor times my. Well, my is really just our stress times our shape property. And we're going to see that in the next slide here for a second. Well, here's the lateral buckling moment. Definitely way beyond what you guys have to calculate. In the graduate program, this calculation does need to be done. It is taxing in its kind of number tracking. That is the hardest part about it. And in fact, I recommend most students write a spreadsheet when they do it. This is about the tendency for the beam to buckle. Now we're thinking bending. How is this buckling? We have our beam here. We're bending it. Oh, only one side buckled. What happens now? Oh, only one side buckled. When I did this, the top buckled. When I did this, the bottom buckled. Why does that happen? What side is buckling? Well, it's always the side that's in compression. So if you take a look at this, we're compressing the top and stretching the bottom. It's the side that's in compression that's tending to buckle. So it seems like a lot of the things that impacted columns could be used in deriving our bending equation as well. If it's really short or something stops it from buckling, we're going to have higher capacities. Okay, look at this. If I bend it, hey Dave, could I use you for a second?
Mm-hmm. Could you ever?
Okay, so see how this tends to buckle? Dave, I want you to just put your finger here. I don't want you to do anything, but put your finger there. Look at how much this is bending now without buckling. Dave?
My finger is very strong.
It's very strong, right? He's a muscle man. How hard do you think you're holding that back?
Less than an ounce.
With very little force, put at that spot where it wanted to buckle, Dave was able to stop it from buckling. In fact, we actually use 2% of the load that's being applied as the thing that would resist buckling. In fact, in our column, if we wanted to stop it from buckling, we could have put something right there, or we could have braced it or blocked it and changed its effective length. For bending, oftentimes we have things connected to the tops of our beams. If this was a purlin or a joist and it was trying to bend, it would be connected to the metal deck. And so a screw right here into the metal deck, for it to buckle, we'd have to crumple the metal deck, which seems unlikely because, like Dave said, it was almost no force here that stopped it from buckling. If this was a beam and we had joists or purlins connected into it, we would have gaps in between where they were supported, but it wouldn't be the whole full length. So this length is the laterally unsupported length of the compression flange. Look, L, the laterally unsupported length of the compression flange. We don't care about the tension side because it's not going to try to buckle. The laterally unsupported length isn't its whole length, it is the length in between where it's laterally supported. When I bend this, its unsupported length on its compression flange is the whole length. When Dave put his finger here, that unsupported length was half of the length. If Dave had stood here and put his fingers in two spots, we would have had a third the length as the unsupported length. So look for things that might be supporting it. Remember I said deck can laterally support something, another beam can laterally support something. So if this is the lateral buckling moment, there is nothing about strength in here. Ooh, IY. Everything else we've looked about has been about the x-axis. What way is this trying to buckle? It's trying to buckle in its weak axes, or the axes that isn't our bending axes. So if we apply a moment about x, it tries to buckle about y. So for buckling, we're worried about IY. So we're worried all about weak axis stiffness. Here's our beam interaction curve. If it is really short or has an unbraced length that's really short, our moment capacity is just our normal MR equation. Remember, M is stress times our section modulus, or our shape property. So our reduced moment capacity would be our reduction factor times our capacity, or our stress, times our S shape property. If it was a rectangle, we would know actually what that S is. Sorry. Buckling is this green line. So when it's really, really long, it buckles very, very easily in the top flange, or we call it lateral torsional buckling, because the bottom doesn't buckle, it actually has a tendency to twist the beam. So see, look at that. It actually tries to twist it. So we call it lateral because it's moving sideways, torsional because now it tries to twist, buckling. And in between a really short element and a really long element, we have a zone where there's some combination of strength and buckling governing the design. Shear. Now, don't worry too much about that. I want you to understand where it's coming from, but you're going to get the same charts that you did for the columns. Okay, shear. For shear, we have kind of a funny stress distribution. Look at this. We kind of get the most stress here at the midpoint and almost nothing in the flanges of our beam. So what we do is we take the average of the low point and the high point and then completely neglect the flanges of our top and bottom chord. So we say that our shear stress distribution is about 2/3 of our peak stress. So if we say that this is at capacity, we actually lower our capacity quite a bit. So we say the VR is our reduction factor times our area of our web, because we ignore our flanges, so it's just this area right here, times Fs, where Fs is the ultimate shear stress. Now, I'm saying that it's about 2/3 of Fy, or 2/3 of our 345 MPa. That's only true for stocky members. There's actually a chart for, depending on what the flange dimensions are relative to its width, and then what the web dimension is and how tall it is. It can get more complicated than that, but most of the time it's about 2/3 of Fy. Again, you're not going to have to calculate this. We're going to look it up. So the total capacity for moment and shear for a steel beam, this is our equation for bending. This is our equation for shear. Bending has a component that is about its depth, because that's its shape property, and a component about its stiffness and its weak axes, which is about its buckling tendency. And shear is all about the area of the web. All right. Oh, I didn't hide these, which makes it less fun to kind of talk through and go through it. But we want to know we want to know the lightest and cheapest beam that works for MF equals 195 kilonewton meters. That has an unbraced length of 3.45 meters. That doesn't tell us how long this beam is. This beam could be 20 meters long. We don't know. We just know what its unbraced length is. So find us the lightest, cheapest beam that works. I have uploaded for you beam bending tables. Let me open that up for you. All right, steel beam tables. And we have something with an MF of 195 kilonewton meters. We don't know what beam they want us to check, but they want us to find the cheapest one that works. They told us that it has an unbraced length that's pretty darn close to 3.5 meters. We could use less than 3.5 meters, but let's get started and find a range of beams that work. Well, this looks like for anything less than 5 meters, we've got massive moment capacities. So look, MR, these are our shapes. They've told us that this is a reduced load. Okay, let's maybe go a few pages in here. We're still talking at 4 meters of things with really, really high capacities. So maybe we need smaller beams than this. We're getting closer to the range we're talking about, but we had a really lightly loaded beam, 195 kilonewton meters. All right, let's come in here. Oh, all right. We were close to 3.5 meters in our unbraced length. It looks like down here, our first element has less capacity than we need. So W250 by 52 doesn't work. We need something with at least 195 kilonewton meters of capacity. So let's go up this chart here. There was our 4 meter chart. Here's our 4 meters. Or no, sorry, 3.5. 3.5, ooh, look at this. 202, let's come across a 200 by 59 works. Great, problem solved. We found our beam. A W200 by 59 works. We're very happy. But they said the cheapest, and we know the cheapest has to do with weight. What if there's a beam that works that weighs less than about 59 kilograms per meter? We should check that out. All right, what's the next one that works? 232 millimeters of capacity. A W250 by 58 works, and it is a little bit lighter. Okay, so we've got a beam that is one step cheaper now. Let's look a little bit more. Let's come up here. Ooh, 197. 197 is greater than 195. Ooh, a W360 by 45. That's quite a bit cheaper. Well, maybe that one is a good choice. Let's go up a little more. Well, this works. A W310 by 52. But it's heavier again. That W360 by 45 seems like a really good choice. At this point, it looks like absolutely everything is heavier than the beam we just looked at. So it seems like a W360 by 45 is going to be the lightest one out of the members that works. Once we know that it works, we could actually interpolate and find out what its capacity is at our 3.45 meters. Because remember, it was 197 at 3.5 meters, but we're a little bit shorter than that. We can actually figure out what it is. And we would be interpolating between 197 and what was the 217 when it was 3 meters long. So we could interpolate to find that 199. Often though, I would probably just say MR of 197 at 4 meter or at 3.5 meter unbraced length would be fine. I will be explicit to you if you need to interpolate. If I tell you you need to find the value, or if I say interpolate to find the results, I am telling you that writing the value for the slightly more conservative approach isn't enough. I want you to interpolate. On the same chart, there's a child crying. Do you have it? Thank you. Well, you can see the sun is coming up in the background. You can see Lake Ontario out there, just a tiny little bit. That's the clouds over the lake out there. On these same charts, look at this. VR, the capacity. It also lists the I of the element. That's weird. We know that might be helpful for something. And beams, we really care about deflection and how much these things move. So maybe there's more that we can do with these charts, but I wanted to show you with a simple example where they exist. To me, the best way to do this is to keep going with that example problem we had for the canopy. We're now being asked, what size do we recommend based on the rule of thumb? And then they're asking us a few more questions. All right, they've said explicitly, assume a uniformly distributed load. Well, we can see that this is the beam that they're asking us to design right here. And we can see we have joists causing point loads on that beam. But they've said we can treat this as a uniformly distributed load, which is really nice because remember we have that handy loading chart that tells us all kinds of things about uniformly distributed loads on a simply supported beam, which is like 95% of the beams that we're ever going to design. I know, I have told you so much stuff over the past few weeks, and I'm going to show you in like half a page how we can condense that down to almost no work. But it's important to know all the work that is behind that. Okay, so what size do we recommend based on rule of thumb or our sizing guidelines? Does a W250 by 25 beam work, assuming the joists don't laterally brace it? So we're saying if this beam is supporting the joists, but for some reason the joists don't laterally brace it, does it work? That's bonkers. The joists laterally brace it, which means we know that in reality our unbraced length is actually this gap. We don't care that it's 6 meters long. The unbraced length is this amount. But first they say, assume its unbraced length is 6 meters. So step 3, we do know the joists laterally brace it. Does it work now that it has an unbraced length that is 1 meter long? And then the deflection criteria is L over 360 for snow load and L over 240 for dead and snow. Does it meet deflection criteria? Is there a better laterally braced beam? Remember, cheapest is everything, and then you could worry about the shallowest. Okay, let's go through this calculation. All right, let's make my screen bigger here. All right. I wonder if I can get this up a little bit further. There we are. I'm just running out of space to write. Okay. Well, we already know that they've already told us, we've already figured out our factored load. So this is a continuation actually of this problem. We've already figured out our factored load and we've already figured out our serviceability loads. So we're already partway there. We've already got some information. So the first thing they asked us was sizing guidelines. So if this was a preliminary drawing set, what beam size would we put on here? Well, we know that D equals L divided by 20 for a beam. And this looks like a beam because it's picking up joists, so it seems like it's doing the normal thing. L is 6 meters. So the D we recommend is 6,000 divided by 20, or 300 millimeters. I'd probably recommend a W310 beam be shown on the drawings in a preliminary set. Okay. The next thing we need to do is find the loads. Find internal loads. we know we have a simply supported beam carrying a uniformly distributed load of WF, or W dead and snow, or W snow. And we have reactions. We want to know, well, first, let's figure out what WF is. WF is the load that beam is supporting. Remember when we were talking about the columns, we said it is picking up half of the joists. Well, the joists were all 5 meters long. So our tributary width is 2.5 meters. So WF is 3.11 kPa times 2.5, or 3.11 times 2.5 equals 7.78 kilonewtons per meter. The distributed load on it for serviceability of dead plus snow. Well, our dead plus snow serviceability load was 2.06 times 2.5 is 5.15 kilonewtons per meter. And snow by itself was 1.3 times 2.5, or 3.25 kilonewtons per meter. Okay, so we have all of our serviceability loads and factored loads acting on this beam. We know that this is a simply supported, uniformly distributed load beam situation. We know that we could manually do method of sections and cut this and find the internal shear force and the internal moment on this at any part in its length. But I've also shown you that we have some beam charts that have told us that R1F equals R2F equals VF max is WL divided by 2, or we're talking about our factored loads here because we want VF. So WF L divided by 2 equals 7.78 kilonewtons per meter. This beam is 6 meters long times 6 divided by 2. If we plug that into our calculator, we get 23.3 kilonewtons. Ooh, 23.3 kilonewtons. That was the load on our column. Interesting. Half of the load on the beam goes to one end, and half of the load on the beam goes to the other. The reaction at the end of this beam, this red line, is our column. It is what the column has to do. This column is supporting this beam. If the reaction at this beam is 23.3 kilonewtons, the load the column's picking up is the 23.3 kilonewtons. So this is nice. This matches what we probably would have inferred. MF equals WL squared divided by 8. Remember, we figured out that, and this was at the ends, and this is at midpoint. So this is at the midpoint of our beam. We have 7.78 times 6 meters squared divided by 8. So we can plug that into our calculator, and we get 35 kilonewton meters. So we need a beam that has the reduced capacity to support 23.3 kilonewtons of shear and 35 kilonewton meters of moment. Now there's also some information about deflection here. We want to know what the max deflections are. Max allowable deflection. All right. Actually, we want to know what the actual deflection is. To know that, well, I'm trying to figure out the best way to word this for you. Because we're going to merge two parts of the solution here. We know we need a beam that is 23.3 kilonewtons of shear, 35 kilonewton meters of moment. We also need a beam. Guys, Mommy's recording a lecture. Okay? Malcolm? Can you tell Duncan no? Thank you, buddy. And remind Daddy. We have a beam that is actually deflecting. So we have actual deflection on our beam. We have an actual deflection on the beam. Hey, buddy. I love you.
Hi, Mom.
Hi, cutie patootie. Okay. Mommy's going to be almost done.
I'm gonna hug you.
Okay, quick. Thank you. I love your hugs so much. I'll come in and give you all kinds of snugs in a second. Okay, sorry about that, everyone. But it is life with small kids during the recovery from a pandemic. Okay, we have the actual deflection, and we know that the actual deflection is 5 WL4 divided by 384 EI. All right, we know that sorry everyone, that door should be shut. I apologize. This is the actual deflection. We know that we have a max allowable deflection of L divided by 240 for dead plus snow, and L divided by 360 for just snow by itself. Well, we know that this is a criteria that we've been given, and we know what L is. 5 is a constant. W is our various load, depending on whether we're talking dead and snow or snow by itself. L, we know. E, we know. The only thing we don't know is I, and it's a shape property. We want to find a member that works. Why not look for a member that has the I that works? So let's say for dead plus snow, we know that the max allowable deflection is L divided by 40. We don't want the actual deflection to go over that. We can just rewrite this. So we're talking about our load of dead plus snow. We can rearrange this. We know everything except I. Let's rearrange this to find what I is. We'll bring I up here and bring this down here. I equals, or I required, equals 5 W dead plus snow L divided by 4 divided by 384 E L divided by 240. Well, that's kind of handy. What if we just did the same thing, but instead of WDS, we did WS and changed this criteria? So we need to meet two different criteria. Dave?
Yeah.
Could you not whistle?
Okay.
Sorry, thank you. All right. We need an I that works for dead plus snow, and we need an I that works for snow by itself, and they have different criteria. So we need an I for both of these. So whichever one's going to be greater is going to be the one we want. Let's plug this in. So I required 5 times our WDS was 5.14. Now here's the thing, E. E is in, oh, I've gone really long. I'm very sorry, everyone. E is 200,000 MPa. We're talking about MPa. That means we need everything to be in newtons and millimeters. Okay, so how do we change 5.14 kilonewtons per meter to newtons per millimeter? Well, we need to multiply it by 1,000 and divide it by 1,000. So we still have the exact same number. Okay, great. But now we need to plug in L. Well, L needs to be in millimeters. So it's 4 meters long, so 6,000 to the power of 4. All right, 384 times 200,000 MPa divided by L, which is again our 6,000 divided by 240. And let's just write it out right now while we can. Everything's going to be the same, including our L. The only thing that's different is this load and our deflection criteria. So 5 times 3.25 times 6,000 to the power of 4 divided by 384 times 200,000 MPa divided by 6,000 divided by 360. Okay, I know, that was a lot. Those are mouthfuls of equations. Let's calculate those. Let's see what we need. Or we get that we need at least 17.4 times 10 to the 6 millimeters to the 4th, or 16.4 times 10 to the 6 millimeters to the 4th. I know, times 10 to the 6th millimeters to the 4th. What crazy numbers we're talking about. We need a beam that has an I greater than both of these values. Well, if it's greater than this, it's by default greater than this. Our beam needs a VR greater than 23.3 kilonewtons. It needs an MR greater than 35 kilonewton meters, and an I actual greater than 17.4 times 10 to the 6 millimeters to the 4th. This is our criteria. All of this distills down to say we need a beam that meets this criteria. Luckily, we have some handy charts that list VR, MR, and the I of various beams with unsupported lengths. The first thing they asked us was, does a W... So I'm going to rewrite this for a second. We're going to write VF equals 23.3 kilonewtons. MF equals 35 kilonewton meters, and I required equals 17.4 times 10 to the 6 millimeters to the 4th. The first thing they've asked us is, does a W250 by 25 with an LU of 6 meters work? And then they've asked us, does a W250 by 25 with an LU of 1 meter work? Let's go to our beam charts and take a look at that. Let's make my calculations small and bring up our beam tables here. All right, let's go to the W250 by 25. That's on the next page. All right. Where are we? W250 by 25. Here we go. Okay, so we're talking about something in this range. Oh, it jumps pages, which is a bit of a pain in the butt. Okay, so we're talking about this line here. The first one, they said, let's talk about it at 6 meters. Well, MR is 20.4 kilonewton meters. VR is 321 kilonewtons, and I is 34.2 times 10 to the 6 millimeters to the 4th. So we can write that out. VR is 321 kilonewtons. Our MR was 20.4 kilonewton meters, and the I actual was 34.2 times 10 to the 6 millimeters to the 4th. That works, and that works. That doesn't work. So a big old no for that beam. I'm going to make this bigger again for you. So I've just written out everything I just looked up for this beam. Let's look up what the values are when it's 1 meter unbraced length. So the length of the beam hasn't changed, just its unbraced length. So 1 meter is less than, so it says that anything less than 1.5 meters, we get to use this. It's basically saying it's fully braced. So a W250 by 25 for an LU of 1 meter has an MR of 95.3 kilonewton meters. VR doesn't change, and the I actual doesn't change. So we still have, let me make us big. All right, we have 321 kilonewtons of capacity. We have 95.3 kilonewton meters of capacity for moment, and our I actual of 34.2 times 10 to the 6 millimeters to the 4th. Yes, yes, yes. I circle it to tell myself that it works. I've listed here what the loads are, here are the capacities, and yes, this member works. There was one other thing they asked us. Is there another member that might be cheaper that works? Let's take a look at our chart here. We need all of the things to work for us. So let's see what we get here. It's got to be cheaper than 25. It's got to weigh less than 25 kilograms per meter. Okay, the 250 by 24 does. Well, let's maybe start from the bottom. The W150 by 13. It doesn't have enough moment. The 150 by 14 doesn't. We needed something that was has at least 35 kilonewton meters of moment. Okay, well the W200 by 15 does. 39.4 is greater than 35. The shear works. Oh, look, I isn't enough. We need a higher I here. Okay, well, it looks like this beam doesn't work and this beam doesn't work. We've got a W250 by 18 here. Moment works, 55.6. Shear works, 247. And I of 22.4. Okay, for a W, let me make this bigger. For a W250 by 18, VF equals 23.3, which is less than VR of 247 kilonewtons. MF equals 35 is less than our 56, the MR was 55.6 kilonewton meters, and I required of 17.4 times 10 to the 6 is less than our I actual of, what's our I actual? At 22.4 times 10 to the 6 millimeters to the 4th. So, they have suggested a beam, but we actually have one that's cheaper that works. We have a W250 by 18. So we can go back to that design team and say, hey, we think we found an even better solution for you. Maybe architecturally you had one that you really wanted to use, but if not, we have one here for you that we think is even cheaper as long as it meets your design kind of criteria. Okay, so that is worked out here for you. I've pulled up the slides so that you can actually look at it as well. So today's tip, plane sections remain plane, bending stress and strain are similar to axial stress and strain, depth and length are the biggest impact on design. Tension resistance is all about stress, compression resistance is a combo of stress and buckling, bending resistance is a combo of bending stress and lateral buckling, shear resistance is all about the web area. Bending deflection can be calculated. So we can calculate TF or CF based on the tributary area. We have beam charts to find MF and VF and deflection based on loads. And we can look up TR, CR, MR, VR, and I required. We can size all our steel columns and all our steel beams. So we have answers. If we were doing a steel beam, we could go out in the world and design it now. I mean, within reason. So I apologize that this lecture was long. I know I rambled a little bit there at one point at the beginning. I will try to post some worked out solutions for you guys. It'll just be a PDF of some more beams. Maybe I take a diagram and solve them out the way we just did. So you have a few more that you can look up and try to work through. Remember, you guys aren't going to do that much complicated math in this assignment, but I wanted to talk about all of these kind of components of it. So have a good week, everyone.